All right. Hi. So we're in the middle of this unit on intermolecular forces and solubility, and I have this 3D water kit that I had bought from 3D Molecular Designs. And it comes with a bunch of molecules of water. It comes with, you can make a molecule of ethanol out of it. And it also comes with a cation and an anion. So I'm going to show you a little bit about those and how it illustrates some of the intermolecular forces of water and of solubility. So you've got a molecule of water. Take a look at this. It's got one red oxygen atom, two white hydrogen atoms. And when you bring two molecules of water up next to each other, they have a polarity, and the polarity is such that the sides between the hydrogens are positively polarized. In other words, there are fewer electrons around them. And if I try to put these together, they don't stick together. They actually kind of repel a little bit. That's because they have little magnets in them. Now, of course, molecules don't really have little magnets in them, but they do have positive and negative charges, and the magnets are helping to illustrate that. If I try to bring the oxygen sides of them together, those would be negatively polarized. They would be two partial negative charges. And again, those don't really stick together. If I hold them gently and bring them together, the way that they do attract each other is with a hydrogen part, which is a positive part, attracting onto the red part of the oxygen. So you can see the red oxygen here of the one water molecule and the white hydrogen on the other one that are attracted together. That would indicate a hydrogen bond. A hydrogen bond is not a covalent bond. It's just an intermolecular attraction. Kind of makes the molecules sticky. They attract each other like positive and negative charges attract. It's much weaker than a covalent bond. A covalent bond would be indicated in this model by the oxygen actually attached, covalently bonded to the hydrogen. And for me to get that off of there is very challenging, even without fingernails, because I trimmed mine recently. I'm not sure I can even get it off of there at all. It's pretty strongly attached. However, the hydrogen bond itself it's attractive, but it's much weaker and it's easy to break. So if I have one particular molecule of water, it's got an oxygen. That oxygen atom can do what we call accept two hydrogen bonds from other waters. Here's a water, and it has a hydrogen which can hydrogen bond to that oxygen in the middle, this oxygen. So the terminology is that this water molecule is donating the hydrogen bond. That's because it's actually covalently bonded to the hydrogen. And this water molecule is accepting the hydrogen bond because it's not covalently bonded. It's just attracted by this strong intermolecular attraction. There would be a lone pair of electrons at each of these two spaces on the oxygen. Those lone pairs are taking up space, and that's why the hydrogens are at this angle of 109.5 degrees. So this oxygen, since it has two lone pairs, it can actually accept hydrogen bonds from two molecules of water, like this. But itself, if you look at it on this way, it actually has two hydrogens, and it can also donate two hydrogen bonds to two other molecules of water, one here and one here. So that molecule of water in the center can actually participate in 4 total hydrogen bonds, and that makes it pretty sticky to other water molecules. So I've got several water molecules in this kit, and if I just mix them all around together, you will find that in general they are sticking to each other. Now, they don't always have 4 hydrogen bonds at any given time, but like if I look at this water molecule right there, it has 3. This one on the edge, which would be like the surface of the water, it only has 2, but it's still being held tightly to those other water molecules. That gives you properties of water such as surface tension. You might have seen bugs that can sort of walk along the surface of the water. And that's because the water molecules are pulling on each other pretty tightly, and they create, therefore, a force that would be required to break that, and you can get a little bit of weight on that. Maybe you've seen where you can take a needle and float it on the surface of a glass of water if you're really, really careful. Of course, the needle is steel, which is more dense than water, and it should sink. But if you can do it just right, it will not break that surface tension and will float on the surface of the water. So that's how water works just by itself. But then when you have a molecule such as ethanol, so this is ethanol. It has 2 carbons. The carbons are the gray atoms. The first carbon is what we call a methyl group. It has a CH3, so it has 3 hydrogens. The second carbon has 2 hydrogens. That's a CH2. And then there's an oxygen and a hydrogen at the end. So if I didn't have this OH group and I just had a hydrogen there, then I would have ethane. I actually have a hydrogen in my little kit here. So if I just put this on there, then I would have ethane. Ethane only has carbons and hydrogens, and those bonds are not very polar, and the molecule is symmetrical. So if I have a water is not attracted to ethane at all. There's nothing I can do to make that be attracted. And so if I try to put this ethane, and I have a bunch of them in the water is going to attract itself, but it's never going to attract the ethane, and the ethane just falls right out of that. Things that are nonpolar, liquids, let's say, that are nonpolar, like ethane, don't really dissolve in water. However, if instead of ethane, now I have to find it. I lost my OH group. There it is. All right, I'm going to pause the video while I fix this. All right, I figured it out. So now if I have ethanol, it has an OH group on it. Ethanol is in fact attracted to water because it has this oxygen with a hydrogen. And when you have hydrogens that are bonded to oxygen or nitrogen or fluorine, they can participate in these hydrogen bonds, which are these strong intermolecular attractions. So how many hydrogen bonds do you think this ethanol can participate in? Do you think it's the same as water, which is 4? Do you think it's only 1 because it has only 1 hydrogen? Okay, it has this oxygen, which still has its 2 lone pairs, so it's able to accept a hydrogen bond from 2 molecules of water. It also has a hydrogen attached to the oxygen, and that's able to donate a hydrogen bond to a molecule of water. So in fact, the OH group of ethanol is very strongly attracted to water, and ethanol dissolves in water very freely. So nice. So let me pick those up. I will not edit that out. So when I have ethanol and I try to dissolve that in water, it is dissolving in water because this OH end is attracted to the water. And even though this ethane end, the 2 carbons with the 5 hydrogens, is not attracted to the water, the fact that we have enough of the OH group at the end attracted will dissolve all of the ethanol in water. And liquids, the 2 liquids, ethanol and water, are what we call miscible liquids. That's spelled M-I-S-C-I-B-L-E. And that means if you have a glass of ethanol and a glass of water and you mix them together, they will mix in completely in any proportion. Completely soluble in each other. And ethanol is, as I'm sure you know, the alcohol that people drink in order to keep their water safe or for other reasons which we shall not go into in this video. Imagine that I don't have any more carbons in this kit, but imagine if I keep adding more and more carbons onto this with C's and H's. Eventually you'll get to a point where this one OH group at the end of the chain is not enough to make that dissolve. So it turns out If I have 3 carbons, it's still completely miscible with water, but when I have 4 carbons and only this one OH at the end, now it doesn't dissolve very well in water. You can only dissolve a few % of that into water. And when I get 5 or 6 carbons, let's say I have 6 carbons with only one OH group, it almost completely will not dissolve in the water. Only a very tiny amount will dissolve in the water. So there's a relationship between how much nonpolar part of the molecule you have and the one small polar part of the molecule. Then and so the attraction there is, again, hydrogen bonding. I guess it's important to note that hydrogen bonding is only the strongest of the attractions. There are weaker attractions, which are called dipole-dipole interactions. Those take place between polar molecules. So the water is also polar, so it has that kind of attraction. The ethane part does not have any of that because it has no polarity. And so, at the risk of messing this up, I'll put the ethane back together again. So this molecule, since it has no polarity at all, has no hydrogen bonding capability, and it has no dipole-dipole capability. But it also does have, and like all molecules, it does have the ability to have these temporary dipoles, and those are called dispersion forces or London dispersion forces. All molecules have those. So they're very weakly attracted. If I have 1,000,000 of these, they're going to weakly attract to each other. But when I try to put them into water, they're going to weakly attract the water, but that's not strong enough to overcome the fact that the water is attracting itself really strongly with these dipole interactions and hydrogen bonding interactions. So it's important to note that all molecules and ions have London dispersion forces. Only molecules that have a polarity have dipole-dipole interactions. And then only molecules that have oxygens, nitrogens, or fluorines attached to hydrogen have the capacity for this really strong hydrogen bonding that we see with water. This kit also has in it a couple of ions. So if you compare the sizes of these two ions, one of them is larger and one is smaller. So they're supposed to represent a sodium ion and a chloride ion. Which one do you think is the sodium ion? So the sodium ion is a cation, and if you look at your periodic table, which I happen to have a copy of right here in my workbook, and if you look at your periodic table, you will see that, so I can make this work, sodium is in the 3rd row of the periodic table, and so is chlorine. So they have the same number of shells. But when sodium gives up its electron, it now only has 2 shells of electrons, and so it's much smaller than the chloride. Also, when something is a cation and positively charged, that makes it draw the electrons closer into the nucleus because of that higher core charge. So the sodium ion is the smaller one, in this case it's blue, and the chloride is the larger one. So if I have the sodium ion, and this kit is demonstrating how that works also, which way do you think the water is going to be attracted to the sodium? Is it going to be attracted with the hydrogen part, or is it going to be attracted with the oxygen part? So the sodium is positively charged. So you would expect the negatively charged side of the water to be attracted. So if I try to put the hydrogen on, again, I see it kind of repels there. I can't really make it work, but the oxygen side is attracted. And the sodium ion, if you try to cram oxygens around it, you'll see that about the maximum number of oxygens you can fit around it is 6. And the model illustrates that. So in the middle of this is my sodium, and it's now surrounded by what we call a solvation sphere of water molecules in an octahedral arrangement. Octahedral meaning there are 8 sides to, if you connected all the points, you would get a pyramid on the top and a pyramid on the bottom, which is 8 sides. And so this is octahedral. There's a water on the top, the bottom, the left, the right, the front, and the back. So that's what you have for this arrangement. And if you notice, all of the oxygens are attracted to the sodium. This is called a solvation sphere, and the attraction between those is referred to as an ion dipole force or an ion dipole attraction. This is a cation, a positively charged ion, and it's attracted to the negatively polarized, the negative side, the partially negative side of the water, like this. So that's an ion dipole attraction. So now if I have the chloride ion, which is a negatively charged ion, which side of the water do you suppose is going to be attracted to the chloride? I'm sure you got this. So the chloride is negatively charged. It's a negatively charged ion. It's an anion. So in the case of water, if I try to stick the oxygen next to that, it's not going to stick. It's going to repel. But the hydrogen side is attracted. And so, again, there are 6 places, 6 sides where you can attach a water molecule. Remember, these aren't covalent bonds. They are just attractions. They're intermolecular forces referred to as ion dipole forces or ion dipole attractions. And here we have the chloride molecule, the chloride ion in the center, and it's attracted to, again, a solvation sphere of water molecules. It might be, in this case, that there is room for more water molecules because you could stick more waters around in here. This model doesn't allow you to do that because it's only got 6 magnets in it. But in an actual chloride ion, you could probably stick more water molecules around and make a solvation sphere of water around chloride that had even more than 6. So again, that's referred to as an ion dipole attraction, and this one with the sodium is also referred to as an ion dipole attraction. This illustrates why ionic compounds such as sodium chloride will dissolve in water, because they exist as these separated or dissociated ions. You have the chloride ion, which is a negatively charged ion. You have the sodium ion, which is a positively charged ion. And when you write these in a chemical equation for the chloride, you would write Cl with a minus, and then in parentheses you put Aq, meaning aqueous or meaning dissolved in water, also meaning dissociated and surrounded by this solvation sphere of water. For sodium, you would write Na plus in parentheses Aq, meaning it is sodium that is separated from water. That's different. So here we go. That's different from when you have sodium chloride as a solid. If I had a dozen of these kits, I could show you what it looks like when sodium chloride is a solid. But when it's a solid, you just have the sodium and the chlorine that are ionically bonded. And that attraction is so strong because it's between a full positive charge and a full negative charge that we refer to that as an ionic bond, not an intermolecular attraction, because it's much, much stronger than the ion dipole attraction of a water to a chlorine. The attraction of 2 ions, a positive and a negative, we refer to that as an ionic bond. And if I had a bunch of these, I could make a cube where you put these all together and they're all attached together, and that would represent what sodium chloride looks like when it's a solid, which is different than what it looks like when it is surrounded by water. All right, so that's my model kit to illustrate intermolecular forces and how they affect the solubility of organic molecules such as ethane, somewhat organic molecules such as ethanol, yes, here it is, ethanol. So ethanol dissolves in water because it has this one hydrogen bonding capable group, but ethane does not dissolve in water because it doesn't have that. A couple of terms I didn't mention. right? This part of the molecule is referred to as hydrophobic. It's not attracted to the water. This part of the molecule is referred to as hydrophilic because it is attracted to the water molecules. So my model kits, even though these are magnets and that's not how atoms really are, they're just tiny charges, the magnets illustrate the kinds of forces that they exhibit. Hydrogen bonding, dipole-dipole interactions, London dispersion forces indicated by not really attracting very much at all, ion-dipole attractions, and even ionic and covalent bonding. The ionic bonding indicated by the positive and negative ions sticking together, and the covalent bonding indicated by these stuck together hydrogen atoms and oxygen or carbon atoms. I hope you've enjoyed this as much as I have. Take care and good luck with your next application of your knowledge about intermolecular forces and solubility.